I want to take a few minutes to actually say a few words about Jerry. I don't know if you guys know this, but Jerry got his degree in pure math at the University of Chicago under Professor Chern. Chern has a bust in front of UC Berkeley, Missouri, Mathematical Sciences Research Institute, very notable mathematician. And Jerry got his PhD under Chern, then went on to work for Bettis Atomic Lab, where he met Eli Gelbard, and together they wrote the seminal book about Monte Carlo to solve the radiative transport. And that was back in '69. So another notable mathematician. So I was very, very lucky to be able to have him as my thesis advisor and be under his very patient tutelage. So thank you, Jerry. Let's see. So I'm going to present some extensions and applications to the fundamentals that you learned this morning. I'm also going to review a few of the fundamentals. I kind of go at it at a slightly different direction, literally, than the morning talk, and you'll see why. I start with a cartoon to hopefully get your sense of humor going, and maybe it'll continue through the rest of the talk, hopefully. But so I plan to review the traditional Monte Carlo concepts because those concepts are the foundation for these extensions. And then I'll talk about perturbation and differential Monte Carlo. Many of you, I think, are working in the spatial frequency domain, taking measurements with modulated light. So I'll describe how you derive the Monte Carlo estimator for that. There's also a temporal frequency measurements that are taken, and I'll derive the Monte Carlo estimator for that. And at the second half, I'll describe how to set up a Monte Carlo simulation using our software, just so that you could run one. You're going to run some this afternoon, but I'll give you a few more details. So just a review of the roadmap to get from the RTE, integral differential equation, to a random variable probability model estimator that will give you a solution that solves the RTE. What we do is we transform, as you've seen, using the method of characteristics to this integral RTE, which describes a collision density psi, and then the solution to that is this Neumann series, and I'll expand on this in future slides. And this Neumann series and a detector function will enable definition of an estimator that will solve the RTE. You saw that the RTE is composed of a transport kernel, and then there's this source term. And if you define the random variable in terms of these components of the RTE, you can ensure that you will provide a solution that is faithful to it. So here's the RTE. You've seen it many times, but just to give terms here, we've got the radiance. It's a function of L, the radiance. US is the scattering coefficient, mu t is the total attenuation, P is the angular phase function, and Q is the source. And the reason why we transform to the integral form is for two reasons. You can show existence and uniqueness of the solution, and you can also represent the solution as a convergent infinite series. So you use the method of characteristics. So this is a PDE method. If you've taken partial differential equations, it's a method to transform a PDE into an ODE, and then it's easier to solve. So you integrate along these characteristic curves, and if you want details of that, it's in the very first reference of your reference list. Bell and Gladstone goes through all the details if you'd like to see that transformation to this integral equation, which is describes psi, the collision density, this collision density is related to the radiance by a factor mu t. And then on the right-hand side, you have this fancy k, which is an integral operator acting on psi, and it's given by equation 3. And then you have this source term, s. So the integral operator in its integrand has this plane k function, which is composed of two kernels, a collision kernel and a transport kernel. And the collision kernel describes at a location r in space how the first component is whether you scatter or absorb. Mu s over mu t is the probability of scattering, because mu s plus mu a equals mu t. Mu a over mu t is the probability of absorption. So this describes the probability at a location r whether you're going to scatter on or be absorbed. If you scatter on, then this describes, P describes the angular deflection from omega prime to omega. And keep in mind that omega has two angles in it. It's got a theta and a phi going on. The transport part of K is shown here, as you've seen earlier this morning. I just want to point out a couple things here. So this gives you in direction omega how to get from r prime to r. There's an integral here to account for varying mu t along that track. So you could have very heterogeneous tissue, and this allows for the definition of traversing that heterogeneous tissue with varying mu t along the path. So, and finally, just to finish up the equation, the integral equation, S represents the density of first collisions. This takes your source term and transports it to its first collision point. So the random walk starts from the source Q. You transport to the first collision point using S, and then at that collision point, you determine whether you scatter or absorb. Over here you see that's a little terminology for it got absorbed. And so then its life has ended, and then you start another photon. But if you scatter, then the angular deflection here is defined by your P function, and then the intercollision distances are determined from this transport kernel. So the benefit to the integral form of the transport equation is that you can rearrange terms and write it just like this. And you can see there's a term here, in series, if you had that term, you'd have 1 over 1 minus x, and if the absolute value of x is less than 1, then you can expand it in a series. Very similarly, you can expand as long as the norm of this operator is less than 1, and there's actually some weaker requirements, you can expand it into this Neumann series right here. And what that Neumann series is that you're interested in getting the collision density at a position r and a direction omega. And how you're going to estimate that is that you're going to take the particles that go to that position and direction directly from the source, those that came from the source and collided once and then went into that direction, and then so on, those that collided twice and went into that direction. And if you take this to infinity, then you'll get the full solution to psi, to represent psi, collision density. So that gives you a solution, but we typically take measurements someplace. We take a measurement I, and we evaluate the solution given some detector function. F. So just as an example, for reflectance, say you had a detector on the surface of the tissue here, it would involve a chi function, characteristic function that just kind of says 1 if you're in the definition of the detector. This detector could be a fiber optic, which has some radial surface area. That would be your delta R, and then it might have a detector NA. That would be your delta omega. And so this characteristic function picks out those photons that have made it to that location and angular direction. And so now we need an estimator. Estimator is a way to evaluate that that measurement, with a random variable. This estimator is comprised of the integral form of the RTE components, S and K. It also includes a detector function, and there are factors in it that potentially give weight to the photon, and you'll see that in subsequent slides. So we have a probabilistic representation of the measurement now with a random variable, and this is evaluated with a measure. Maybe you can think of this as it's something that arises from the probability density functions that compose S and K. So we evaluate I by taking the expectation of this random variable, and we do this over n, which is the number of photons launched. So let me give you an example for reflectance. We have a source, say, on the tissue surface and a detector on the tissue surface. And we use something called the modified terminal estimator. The reason why it's called modified is there's a terminal estimator, but because we're detecting on the boundary of the domain, we're actually interrupting a tract here. So in the source, the photons come in and collide. These are actual real collisions. And P is just a short, PI is just a short cut representation for a position and direction. And then on this last track, as the photon exits, we actually put something here at the intersection called a pseudo collision. And just for notation, we take the last real collision and then superscript it with 1 to represent the pseudo collision. So it looks kind of crazy here, but here's the random variable to estimate reflectance for us. And you can see it's comprised of these factors. We've got factors of S terms and then K terms and then the detector function. And in the numerators are the S and Ks of the RTE, and in the denominator it's the S and K that's actually rolling as the random walk rolls. And this detector function is the one that I showed on the previous chart with the chi function, picking out reflectance. So if we were to do an analog random walk process, this adheres directly to the S and K of the RTE. So we do exactly what the RTE says. We say, okay, first collision, did it scatter or absorb? Or it absorbed. Okay, end of photon. Go to the next one. And the way we transport and angle deflection at subsequent collisions is identical to that in the RTE. So all of these factors end up being 1 when you run an analog random walk process. And this ends up being a binomial estimator, where you have a photon come in, its weight stays 1 through its whole process. It might get absorbed. It might exit outside and not be in the detector, but it might exit in the detector, and if it does, it scores 1. So here's a little video. Might stop it at different parts. So this is using an analog random walk, and I stop it there because this little that random walk ended here, and what this represents is that's where it got absorbed. And then subsequent ones got absorbed. And then let's keep going. So this shows, let me back up a sec. This shows as what those absorbed, they're being tallied in a voxel. So all those voxels that have an absorbing event in it, what it looks like as the number of photons increases. And I think I go up to, whoops, I go up to there. So this gives you a light distribution within the tissue of the absorbed photons. Now let's add a detector. And here I'm showing for this detector, source detector separation, the photons that actually contributed to that detector. And we call them kind of photon bananas, if you will. It'll show you kind of the light distribution. So that gives you an idea of how the analog simulation would provide results. And just gives you an idea of what it looks like in a simulation. So an alternate, we heard about discrete absorption weighting this morning, and it's an alternate method to account for absorption. And it has pluses and minuses. It depends on the situation. So a lot of times it can reduce variance, but it runs a lot longer. In this method, we disallow the termination of photons, and that's why it runs longer, because the photons, instead of stopping when they get absorbed and starting a new one, you run it till it exits the surface of the tissue. And so in order to adjust in an unbiased way that we're not terminating those photons, that we have to modify the photon weight. And so this shows what the photon weight, using this modified thermal estimator, each one of these factors are going to be mu s over mu t evaluated at the location relevant to this factor. And so if you were to have a homogeneous tissue, this would end up being mu s over mu t to the power k, k being the number of collisions prior to exiting the detector. And so this shows kind of how this would run, showing that it would start with a weight 1, and each collision, that weight gets degraded by this factor mu s over mu t, and so forth until it gets detected. So here's a movie of that. And right now I'm not showing the weight degradation, I'm just showing the path, and then it'll show how that path weight is degraded discretely at each collision point. And then again as the number of photons, and then as this detector is added and it moves inward. Any questions? Lawson, you're not supposed to have a question, Lawson.
Can you go back to your analog video?
So you want me to play it?
Yeah, just play it and stop it at n equals 10 or n equals 100.
Like here?
A very simple question.
Uh-oh.
Oops.
Okay, let me see if I can do that. Okay. How about that?
Yeah.
Okay.
Great. So I only see 5 specks there.
Yeah.
Yeah. Why is that?
Well, you mean because there's 10? Well, yeah. Okay. Well, because of the optical properties in this particular situation, and so at each collision point, it's a roll of the dice. I'm actually picking a random variable between 0 and 1, and I'm comparing it against mu s over mu t, and if it's less than that, then it scatters on, otherwise it gets absorbed. And so that's why it's dependent on the,
So what happened to the other 5 photons?
what happened to the other 5? Well, they continued on. They continued on and exited the surface. Oh, is that what you want to know? Okay, yeah.
We're only looking at the subset of photons that actually deposited their weight in the media,
Right.
as opposed to
Yeah,
photons that
not
just left.
every photon dies in the medium, unless it's really, really absorbing, and then you wouldn't get anything reflected back out.
And so, in analog, I think it's important to note that each photon, at most, contributes to a tally at one location within the medium, whereas in discrete absorption weighting, the photon has the opportunity to contribute to a tally at every single collision.
It's true. It's true. That very kind of, and you could just also see it by the, I think I have to run it before I can change page. Okay, let's go back. Yeah, so in this very convoluted path, every time, if it were to hit a voxel again, loop back on itself, it tallies again there. So yeah, it has that advantage, but look how long it's taking.
Right, so the corollary, yeah. So clearly, when you showed the photon bananas, or you even just see the internal distribution of light, for a given number of photons, you get a more filled
Yes.
or smoother
Yes.
representation, but it comes at a computational cost.
It does. It does. Okay.
That's my job. I've got to egg people on.
He's trying to get around.
So we're solving for the steady state solution here, but so how does that translate into that you essentially have a certain amount of power flowing through each point per unit time? So if you were to, say, try and figure out for this length of time, how much absorption do I get, or how much, flux do I get through this portion?
Yeah.
How would you translate that?
Okay, so if you're looking for time-dependent results, which it sounds like you want, so if you were to look at the fluence, then each one of those voxels, you would take note of the path length from the source to when it collided. In discrete absorption weighting, it has to collide in that voxel to tally, and you would then use that path length and the speed of light in the medium, has to be divided by n of the refractive index mismatch, and then you would get a time, and you could tally that to a time bin and get a distribution. Same for reflectance. I could have noted the path length upon exit the detector, and I would transform that to time, and I could get a reflectance versus time function.
So say if we're, if we're not actually using a detector, say if we're at the point where we're just looking for the steady state distribution of light in the medium, say before, in your animation, before you introduce the detector, you can see that you have that steady state distribution.
Yeah.
So essentially to estimate the amount of absorption at any given point, you would have to apply that speed of light to say after X amount of time, this is how much has gone through this point.
If you wanted it with respect to time, then yes.
Okay.
But if you just wanted to know the total absorption, then yeah.
Okay.
Yeah.
All right.
It's-
Are equivalent. And so you can calculate time from path length, and that's generally what we do.
Is your objective here to try and quantify what, say, a potential temperature change or total amount of energy? So, yeah, so one thing you can do is that you actually don't need an absolute number. You know that, say, if you put in 10,000 photons, you can figure out what fraction of the energy of those 10,000 photons get deposited in a single voxel or a group of voxels if you're looking at a volume, and then you can scale that because it's a linear scaling, right? So I think that in that problem, you don't necessarily need the temporal response. You just need to know how to appropriately scale your source strength relative to the subset of amount of energy that gets deposited in the volume that you're considering.
Yeah, and I wanted to mention that, all of these estimates are divided, if you noticed, 1 over n. The expectation is 1 over n, the sum of the tallies. So in a Monte Carlo simulation, if you send n in, all of them are going to get divided by n, and they get, so in a certain sense, normalized to 1. And the difference that I show when I'm increasing n is more to show the errors that would be result when you use less photons or more photons. It would reduce, that error is going to reduce, as you heard earlier this morning, as you increase n. So that was just meant to show that, rather than, not in a physical sense, that a source is actually sending in that many photons or something like that. Sure. So I'm going to shift gears and talk about perturbation Monte Carlo. This is a method that allows you to determine a change to whatever measurement you're interested in due to changes in the optical properties within the tissue. And, oh, Gideon's online. Sorry, I should probably close Skype. Oh, okay. So say you have this tissue, and there's a region in it that has different optical properties. Maybe it's a cancerous area, tumors forming there, and you're interested to see what the change to your measurement is based on a change to the optical properties here, and I've just kind of notated them generally as alpha. So one way you could do it is that you could actually run a simulation through this two-region problem, in which you change as you're tracking the photon, you cross into this region, you modify according what you're doing in your random walk according to the optical properties here, and then when you leave, you go back to the optical properties here, and you could get an estimate of I hat. But this would be computationally costly because you have to run another simulation. So PMC allows you to evaluate this I hat or due to any change in alpha very quickly. The way it does it is that we run a baseline simulation through the homogeneous, or maybe we could call it healthy tissue, and we store pertinent information into a database. And then and this could be done for any kind of, I show reflectance versus rho here, but it can be done for fluence, radiance, temporal frequency, spatial frequency, any kind of detection. So we save this information to a database. And then what we do is we read this database and we apply a certain weight that provides an unbiased estimate of this I hat. And what is applied to the photon weight is something called a radon-nicodine derivative. And this ratio of the measure again is the thing that that arises from the PDS that comprise S and K. In the perturbed system due to the measure in the background healthy tissue system. And this will make more sense when you see actual equations for this. So you can use this to estimate I using the background set of random walks. You apply this weight factor to the random variable and get an estimate of your perturbed response. So let's look at something definite. Let's say we're using discrete absorption weighting. And we're tallying this background rate, mu s over mu t to the power k. Each photon, each one's going to have its own number of collisions k, and we add them all up, and we divide by the number of photons launched, and we get an estimate of reflectance. The pertinent information that is saved is the number of collisions in this region of interest and the total path length that each photon traversed in that region. So the application of the radon-nicotine is seen right here. You can see this is the C term. This is a mu s over mu t portion. It does not have the P term because we're not perturbing G. If we were perturbing G, we could do a ratio here of that term, the P term. But since we're just perturbing mu A and mu S, we have this term here. It's the perturbed optical properties over the healthy tissue optical properties to the power j, j being the number of collisions that photon experienced in here. And then here you see this, the t correction. We have mu t hat, e to the minus mu t hat, path length L, and if you were to sum over all path lengths, it would be the total path length S in the perturbed region. And then, so that's the t in the numerator. You'd have a t hat in the numerator, t plane in the denominator. And so these are the weight factors. So I just read that database. I say, give me what j is, give me what s is. Now I can estimate, given I know what my delta A and delta mu s are, what my change to reflectance is. And you can see in this plot, the baseline is red. I ran a simulation, a perturbed PMC evaluation with increasing the mu A by a factor of 2 and then decreasing it by a factor of 2. And you can see that there's this correlation. They kind of track. These little bumps in it are tracking, and that's actually to your benefit. And I'll tell you why about the benefit in the next chart. So before I do that, we can also get differential information. We can take derivatives of this perturbed estimator for reflectance and with respect to the optical properties of interest, and now we have sensitivity coefficients. And this allows us to use a gradient-based optimization method and to determine those coefficients. So the way that we do that is to find the derivative of an estimate. We take the expectation of the derivative of that estimator, and I just show that it's a very direct, you just take the derivative of this with respect to delta mu A or delta mu S, and that gives you your estimator for the derivative. You can also do second derivatives, cross derivatives, and get covariance matrices. So the advantages of both of these is that you're using one single random walk. Here's the differential plots, and the same bumps are happening. And what's happening is that the correlation, because you're using a single set of random walks, that correlation in your estimates is actually has a smaller error than if you were to run an independent simulation with those optical properties. We also can run a bunch of different perturbations simultaneously. And for instance, I just ran 10,000 photons, and it takes about 5 minutes. And then with PMC to evaluate the same thing takes about 0.7 seconds. So quite a bit faster. And again, we can do a gradient-based optimization, which actually I cover on Thursday. I'll show you details of that. So that's kind of a quick overview of PMC and DMC. And I'm going to move on to spatial frequency domain estimation, unless there's any questions. You have a question?
I was just curious about, so you're talking about perturbed tissue, but does that also include how you simulate different kinds of tissue?
Well, you could. I mean, if you, for instance, you could, it's more, I think I now understand. I think it's more to see what is the resulting measurement if some of the optical properties that you assumed in your baseline system were perturbed. This is a perturbative method, so it's going to work actually best if the changes are small.
Okay.
Small in magnitude and small geometrically too. But if you were, like, for instance, if you had a tissue that was very heterogeneous, had different constituents that you were trying to model, then you could run a very heterogeneous tissue definition and run a simulation through that.
Okay.
I guess maybe I can provide a little bit of context. So we know that, at least compared to, say, analytic representations or solutions to the RTE, Monte Carlo can be quite computationally intensive. And so if you're interested in understanding how maybe your signal may change, or how maybe your deposited energy may change based on a small change to your system, rather than run a second independent of Monte Carlo simulation, if you ran your initial Monte Carlo simulation and saved this biographical information in literally, a small, maybe 2 orders of magnitude faster in time, you can actually get a change of, the impact of a modification of your original system, rather than run an independent simulation. And not only that, because you're using the same set of biographies to generate the new weight or the perturbed weight, whether that be a reflectance measurement or energy measurement, you benefit from the correlation between the photon biographies of the baseline and the perturbed system, and therefore actually your ability to detect differences is actually enhanced by doing this perturbative method rather than running 2 independent simulations. So that's kind of what motivates this.
Yes.
And then it also then opens the door for actually using Monte Carlo to resolve inverse problems, because doing optimization requires information on derivatives. And if you try to run independent Monte Carlo simulations, that will not be tractable, not in terms both in computational cost as well as precision, because you don't have the correlation between independent simulations. So that's kind of the overall motivation for why we're interested in such methods.
So not to get like too super mathy or anything, but when you talked about the radon-nicodime derivative.
Yeah. Well, you see it here.
Sure.
Yeah.
Right.
Yeah.
So I suppose whenever you take that between 2 measures, we have to make sure that one measure is absolutely continuous with respect to the other.
Yes, you do.
Is that something that just doesn't come up with this? Like, do we just not have any sets of zero measure?
That caveat has to be adhered to. So the zeros, if there are zeros in the denominator, they have to be zeros in the numerator. So,
Okay.
Yeah, but in this particular case, we don't have that problem.
Okay.
Yeah. I'm going to switch to spatial frequency domain. How many people are actually using spatial frequency modulated light? I thought I heard somebody in intro. 2 people. Okay, good. Oh, 3. Yay. Okay, so somebody is actually using this. So as you guys know, the tissue surface is illuminated with a spatially modulated pattern. And usually it's along the x-axis, although for generality it could be along the y-axis as well. And then we measure the amplitude change and the phase change of the resulting diffusely reflected light, and that gives us information about the tissue subsurface characteristics. So how do we get to an estimator from the RTE for the spatial frequency domain? What we do is we Fourier transform the RTE into an integral RTE, not yet. we Fourier transform, and we get a Fourier transform RTE for radiance. And then we transform that to an integral form, and then we get an estimator. So I want to kind of preface this that some people run a spatially resolved result. Either they use, they can use diffusion, they can use Monte Carlo, and then they use a discrete transform on that to give them the results for the spatial frequency domain. But that transform actually there's just discretization errors, and also there can be some artifacts that come from it. So this is a more direct way to use within Monte Carlo to estimate those spatial frequency domain estimates. So just to see how we do this, so we start with the time-independent RTE. We do a 2D Fourier transform over the transverse directions, x and y, and it ends up being this equation. Now we put a little hat on the L because it's been Fourier transformed. We have this function that I kind of highlight in red because it's important. Also notice that there's only dependence in z now. So we have an omega z, everything z, not r. And L hat is given by this equation here. So similar to transforming the RTE, we do the same thing here. You go along characteristics, there's an integrating factor to solve the ODE, and you end up getting a collision density equation, integral equation for the collision density. I'm putting hats here too. And here are your K and S's. And note that there's this dependence on z now instead of r. This factor in red is the key thing that's different. And so if we were to estimate reflectance, we'd use this modified terminal estimator. But if we were to use analog as your random walk process, you can see that if these factors are going to result in an extra term here. So each one of these is going to have an extra term. So you're going to have a product here, and then you're going to have this little pseudo-collision track at the end. And if they cancel out, and so you end up having something like this, which is e to the minus 2 pi I, your spatial frequency, and then the x component of the location that you exited minus the x component of the source. And so if you were to start your source at 0, 0, 0, then you would just tally e to the minus 2 pi I, spatial frequency x, xk superscript 1. Any questions about that? Are you guys running Monte Carlo? Okay, so you're familiar with this tally. Okay.
So Carole,
Yeah.
so maybe another way to express this, so typically when you're on conventional Monte Carlo and you get spatially resolved diffuse reflectance, if you want to determine the weight at any given spatial frequency, you would have to do a Fourier transform and then read off the value of the Fourier transform for a given frequency.
Yeah.
Right. And then, but here, essentially, you run a single Monte Carlo simulation, and for every photon that exits, you essentially look at the, for lack of a better word, migration in the x direction, away from the source, and then essentially you assign to it kind of a weight, a complex weight that encodes basically the spatial phase that photon
And
exits, amplitude and phase,
Yeah.
but the 2 pi I fx
Right.
xk is essentially the number of radians, spatial radians that the photon has migrated and looking at the number of cycles relative to fx.
Yeah,
Right, okay.
right.
So
You get
that's
your
what
phase
it's doing
information.
physically.
And the attenuation
Right.
too, to the amplitude.
Right.
Yeah. Yeah, so this is actually the derivation of the estimator was done by Boston's student, Adam Gardner, and they call it sometimes the shortcut method because it avoids the whole discrete Fourier transform done after the fact and is a more direct way to get the estimate.
Another comment is that in a discrete Fourier transform, you have frequency bins, right?
Yes.
And
There's
here,
binning
there's
problems.
no binning
No
involved
binning.
here. You can define your entire array of fx's that you're interested in, and you actually get the tally for that fx
that.
without any
No bins.
discretization.
Yeah, even in R of rho, you're going to have a rho bin, and then you're going to Fourier transform. With this one, spatial frequency, you hit it right with the spatial frequency that you need at the x location that you exit. No binning. Okay, so I'll move on to temporal frequency domain. Anyone doing temporal frequency domain? No, huh? Oh, okay. We do it at Beckman Laser Institute. And so here we send in a amplitude modulated source, and then we measure the change to the amplitude and the phase shift. It gives us information about the tissue subsurface characteristics. So again, we follow this roadmap, except for we're going to use the time-dependent RTE. We're going to Fourier transform that with respect to time. We're going to change that to an integral RTE, and then we're going to have an estimator. So here's the time-dependent RTE. And a Fourier transform of that with respect to time gives you this equation here. It's very similar to the regular one, the regular RT, except for you have this extra term here. And you have a Fourier transformed radiance term here. And this was done by Testorf back in '99. So again, we do the method of characteristics. We transform this into an integral equation, and both Adam Gardner's paper and Testorf's paper, I think, provide details of how to do that. And now we have a K and S term that looks like these. I've highlighted in red what's different. And when you plug it into the modified terminal estimator, I don't show all the cancellations, but basically you can envision that each of those factors are going to present an exponential with that term in red. And then we get a final tally here. We convert the path lengths into time. And that's pretty much it. It's pretty straightforward. Okay, now I'm really shifting gears. Is there any questions about that? Okay, I'll keep going. So I wanted to describe a little bit about our software because you're going to be using it this afternoon. And we have this conventional Monte Carlo. We call it the conventional Monte Carlo. It's going to be representing the capabilities that were described this morning. It resides within a library that we have a command line utility that uses that library, a MATLAB interop, and a GUI interface with a Monte Carlo panel. These are all this has got the most capabilities, second most. This is the least for maybe more of the novice who wants to just run something easy. And our labs today will have examples of all three. So in order to get the Monte Carlo command line, you could go to a home website, and then there's a tab called Developers, and then on that page, it's click here to go to the GitHub site. This is where we host our software, and then there's a link there, and you can download the software. And we give a lot of sample infiles, and in this one, we show all the detectors that we have defined. And then we have documentation on our website about how to edit these files, run it. You can run a series of parameters with one command in a parallel way. So just quickly, I just want to show some of the options. You show how many photons you want to run. If you want to seed the simulation, this allows you to reproduce your results if you seed it with the same seed each time. We use a Mersenne twister as a random number generator. You can change your absorption weighting type from discrete, analog, and then to something continuous. We have the Henny-Greenstein function, phase function. We also have a bidirectional, which is nice to debug new theoretical ideas. Databases are if you want to define a database to do PMC. The ability to do Russian roulette. This is a way to kill off photons in a fair game. You wait till the photon weight gets below a threshold, and then you roll the dice and play this game in which with a certain probability you kill that photon, with certain probability you boost the weight and let it keep going. In all the simulations that I've shown, I did not turn on Russian roulette. And then we allow enable different source definitions, a very simple point source with a direction straight in positive Z is into the tissue. And, but we have a myriad, Jonica wrote a myriad of different source definitions for most applications. You can have embedded sources, you have surface sources, you have sources above that come in. So yeah, we have got, and that's all documented there's a documentation, and then there's a link, capabilities and implementation of Monte Carlo. Click that link, there's a sources section. And then we have different kinds of tissue. We have a homogeneous tissue, we have a multi-layer tissue, we have a single inclusion tissue where you can have an ellipsoid or several ellipsoids or a voxel in here. And we can have air up and above and below. And then we have different detectors. We have RFFX. RFFX is different, like I said, with binning. RFFX, you evaluate these at the specific FX that you define. And then RRO, for instance, though, has bins. So if you define these bins, you're actually going to tally when the photon comes out a detector region with a row cylindrical coordinate in these bins. And this is similarly to spatial frequency. The temporal frequency is tallied at the temporal frequency that you select. And this Monte Carlo command line can work on Linux, OS X, Windows, of course. We have instructions on how to run it on Linux. It's slightly different. And then I list here the assumed units in the software. So something you're going to see in the GUI today is something called scaled Monte Carlo. And I want to describe that this is a different beast than conventional Monte Carlo. What has been done here for the purposes of presenting a very quick result was initially performed by Keenly and Patterson. What you do is you take the results of a Monte Carlo simulation for R of rho and time, and they chose these optical properties, and that R of rho and time is saved. And then through weighting described in their paper, as you change optical properties, you take this and you kind of shrink and enlarge the domain, and you're able to get results for different optical properties very quickly. But just keep in mind, that's not like, so when you choose this, it's called basic. It's a pull down called basic Monte Carlo. You're not actually running a simulation, you're taking results that are being scaled. And we coded up the basic, but then a graduate student here, Michele Martinelli, expanded on that using non-uniform rational B-splines and adaptive binning. He found that in far times and row bins, the bins weren't big enough to ensure kind of a uniform variance across the whole result domain. And so he made these adaptive bins to make that more uniform, and then he applied a non-uniform B-spline to smooth out the results. And that's called the NURBS scaled Monte Carlo in the pull down. And you'll be using those quite a bit in the labs. So I just wanted to show the distinction. So hopefully you've been exposed to some extended ideas, perturbation, differential Monte Carlo, how the spatial frequency domain Monte Carlo estimates were derived, how the temporal frequency domain Monte Carlo estimates were derived, and then how you can run a Monte Carlo for yourself and execute it and plot the results. So thanks. Any final questions? Oh, sure.
So are we considering a point detector here throughout in the simulations?
A point detector? Well, no, it depends on what you're like for instance, if it's R of rho, then it's a bin. So I'm collecting, well, in cylindrical coordinates, we also have R of X, Y, and Z.
Oh, so we can mimic the most practical
R of X and Y. So there are different options for the different kinds of coordinate systems that you want to work within. If you have something that's cylindrically symmetric, like layers, a lot of times people use the cylindrical coordinates. But if you have heterogeneities in the tissue that break symmetry, then you would use R of X and Y, Cartesian coordinates. Yeah, so we have those.
Okay.
Yeah.
Yeah, I just want to emphasize that the capabilities that you see on this graphical user interface, I mean, Carole had this beautiful image a few slides back where she kind of abstracts out our entire software base and then looks at subsets of that. But what you see in the GUI is really a small subset of all of the capabilities of the virtual tissue simulator. And we have actually a very general and very powerful Monte Carlo engine that you kind of have to go into the command line to edit. Carole is here to guide people with that. We've collaborated with many groups to customize or to basically help with the configuration of our Monte Carlo solver to address specific questions that they have in their laboratory. That's one thing. The other thing I just want to mention is Carole mentioned about scaled Monte Carlo, and I think there are a couple things that really bear emphasizing. Number one is that, as both Professor Zhao and Carole's emphasized, that when you do a Monte Carlo simulation, you're estimating the mean of a solution, and so any result you get out has an estimate with a standard deviation associated with it, or variance associated with it. Now, what scaled Monte Carlo does is that it doesn't actually consider the variance at all. You've run a Monte Carlo simulation. Hopefully you've done it with lots of photons, so the variance is small, but it's still present. And then you apply these scaling relationships to scale it for a different system. But you're only scaling the mean. And depending on whether that scaling is expansive or contractive, the variance can really potentially blow up. And so it's not a rigorous Monte Carlo simulation. It is It is an estimate. And you can show that the scaling makes sense from an analytic perspective of the radiative transport equation, but it's still something that needs to be treated with some care, number one. Number two, even though the scaled Monte Carlo is done in this spatially resolved domain, we've also implemented scaling relationships that allow you to get, it's done in both spatial and temporal domain. We're also able to transform the results to both spatial and temporal frequencies, modulation frequencies. So the GUI, you'll have the opportunity to run scaled Monte Carlo for any solution domain that you may be interested in, whether it's spatially resolved, temporally resolved, spatial frequency domain, or temporal frequency domain. So if you have any questions about how you want to configure our Monte Carlo code to solve particular problems of interest to you, feel free and
Yeah, if you're interested in
approach us.
getting started and you don't know how to, first steps, come by and see me and I'll get you started.
Other questions?
I was just curious about the parallelization in your
Yeah,
simulation.
yeah. Oh, so I don't have an example here, but the way that we set it up, I think I wrote it here in parallel spin. So in the command line, you can actually give it a parameter sweep. So if you define your tissue, let's just keep it simple. You have a homogeneous tissue, and you, in your infile, have defined a mu A and a mu S in that tissue. You can actually, in a command line, at the end of the command line, add a command that allows you to specify running simulations for mu A, say, in these increments, and mu S in these increments. And what the code will do is, if you are on a parallel processor, it'll put out to each of the processor, and they will run. Actually, the reason why this capability is in here is that David Kucha, who you'll be seeing on Thursday give a talk, he wanted to create a Monte Carlo table lookup for a variety of different mu A and mu S values, and so he just created this sweep and one command, and he set it overnight on a parallel processor, and the next morning he had his lookup table. So that's why it was entered in. He was our software architect when he was still working here. So it's fine.
Have you looked into accelerating it with GPUs at any point?
Not yet. But yeah, there are definitely groups doing that, and that would be a great thing. Yeah, because it's embarrassing. Monte Carlo is called embarrassingly parallel. They actually use that term, so there's no reason why we shouldn't be going parallel.